hear today about the contribution of the new material standards for ductile irons and Austempered ductile iron.
Thank you very much. Good morning and thank you for listening. My name is Franco Zanardi, I'm coming from Italy and... sorry. Okay. Okay, my name is Franco Zanardi, I'm coming from Italy and I belong to the Zanardi Fonderie organization. Our company is a specialist since 1982 in developing ADI materials. And the aim of my presentation is to give a contribution for a more modern approach to definition of the standards, because what we have now as international official standards are very poor in comparison with what the ductile irons are really able to give. Co-authors are professors of our universities in Italy that are cooperating with us on this field. Okay, so in fact, some non-conventional standards do exist. In the yellow row, you see the high silicon grades. Then in the middle, you see the Cibodures cast of Georg Fischer and our IDI, that is a patented material quenched in soil bath but without alloying, and Fiat standards that are existing since the 70s, and also at the end the R.Cozzi Cibodur, the grade 700. When we are talking about the treatment on ductile irons, we have two approaches. The first approach now I explain is our IDI material, where we start from a ferritic unalloyed conventional ductile iron that you can machine before the treatment at 150 Brenner harness. Then we make austenitization in the intercritical range, as Professor Nofal told before, for IADI, and so we leave some protectoidic fluoride in the matrix. Then the austenite is the casting, and then the austenite is quenched into a soil bath. Being unalloyed, we cross the pyritic nose, obtaining a matrix of ferrite perlite that is interconnected and with no isolated isle of ferrite surrounded by perlite, and very important thing, we have no copper or tin segregating at the grind boundaries. The conventional soil bathing treatment is the one of ADI, where we start with low alloyed ductile iron in order to give the hardenability to be quenched, avoid the barytic nose, and then to cross the ausferritic nose, obtaining the well-famous ADI as ausferritic ductile iron. That, as I told before in the last presentation of Professor Nofal, is machinable, provided it is done in the right way. This non-conventional standard, you see, can be best fitted with the black line on this diagram, elongation versus ultimate tensile strength. The black lines that are one for polytic ferritic grades, and on the right the austenite, ausferritic grades. The green lines represent the conventional standard that you find the ISO standard. Of course, when we are talking about non-conventional standards, such as I-silicon or Cibodur or our IDI or Fiat grades, of course we are obliged to fulfill the requirements of these grades, that the point represented by A5 and RM is on above the black lines. And if we want to be allowed on our castings to have a Brenner hardness range of, for instance, 30 Brenner points, points. To be able to do that, our couple of A5 RM should be on the above the other line, the red one on the left, representing the cast material, and the blue line for IDI and ADI representing the heat treatment material. This line guarantees the ability to fulfill the minimum properties and to have a Brina handle range around of 30 Brina points. So one way to specify the material is to use a quality index that is a combination of tensile strength and elongation that assure that you are on this region. And so specification should be done by material quality index, grade, that is the minimum strength or the minimum hardness on the casting, and uniformity, that is the Brina handle range the designer allow on the casting. So this is what I said before, how I suggested to specify the new grades for the standards, or specify minimum hardness or minimum strength, the quality index, and the uniformity. Okay, then we go to the field that has been explained in other presentation very well, that is this defect tolerant design. An imperfection, a defect in our casting has a very different effect if we are talking about high plastic deformation or we are talking about fatigue. So I suggest that when we are considering large deformation, that is how it is in the tensile test, we should not use test probes with some defects, as they are sometimes in the castings, as a material quality test. This is a test of material quality and defect at the same time. So while when we are talking about fatigue, fatigue is a local property. If I have a failure on this side, independent on the other sides, this will make the crack start, and so the fatigue will be affected the casting. This is simply a comparison of the Paris curve, the blue one of ADI tested in with our material in Padova laboratory, and the red one that is the Paris diagram of the best steel for making the high-speed trains. And you see how ADI competes very well in the crack propagation rate because of sphenoids. And this was also recognized by Deutsche Bahn in the early 1999. So it is important to consider that the fracture mechanics applies to cracks. And we have the values of the threshold value for the stress intensity factor, the delta KTH of the previous presentation, for the non-propagating cracks, propagating under cyclic loads as they are in them, and the fracture toughness K1C. In XDIs casting, I call always XDIs to intend every kind of ductile iron, normal, paritic, ferritic, silicon, or Austempered. Imperfection and defects are rarely shaped as cracks, as happens in steel, for instance. And so the stress concentration factor, KT, could be not infinite, could be at a limit, could be calculated or assumed. And so this is very important. So to change the Kitagawa diagram, to complete the Kitagawa diagram as is teaching Padova University, that is assisting us in these matters. And so we can have the first, the unnotched fatigue strength then the delta KTH, that is the obliquous line, but the fatigue limit cannot go always under the full sensitivity. This diagram represents our experiments on all the iron that we tested from ferritic, high silicon ferritic, IDI, and ausferritic ductile ions. The fatigue limit are notched, and this is also the delta KTH, the threshold value for all the same material. And you see that we always make the same test with a 42 chromium moly 4 catch-on temper steel, so to be sure that the same procedure is also applied to the comparison steel. Instead of Sharpie test, we propose that a constitutive curve are used because this will be much better for the component itself when we are testing at high particle deformation. These curves can be described by the VOS approach that we are using now at our company in order to give a numerical value to the shape of curves, also for process control. And this is a representation of the complete constitutive curve that we did with the Cassino University in Italy, Professor Bonora, with the ADI 1050, where we have tested at quasi-static and at the Hopkinson bar, 1000 seconds -1 strain rate, at different temperatures, -60, 70, and room temperature. This enabled to design at shock at high impact loads our castings. So my vision is that the tensile test of separatory cast from the casting test probe shall show a quality index above a specified limit, as I showed before. The position in the casting where to cut the test sample should be left to the discretion of the manufacturer to be sure it will be sound, but designers should be allowed to ask for fatigue tests using a test sample cut from the most critical position in the casting. Hardness value measured on the test probes will enable us to determine the minimum hardness able to guarantee the ultimate tensile strength, and also the shape of the curve should be very well described by the numerical values I took before. And these are represented, you will see in our presentation, my proposal for the new grades defined with this approach. Thank you very much for your attention, and this is a list of situations where we are cooperating with other people in the field of the European community for research on this field and for support of pre-normative work. Thank you very much.
Thank you, Mr. Zanardi, for your presentation. Any questions from the auditorium? So, it was a lot of information on one point. Maybe one question. You discussed about some problems with some small cracks or something. What is the influence of inclusions? Do you have any idea how to handle inclusions? Yeah,
we normally cooperate with our customers in co-design using the Murakami approach. So we define the defects that are allowed in the given section, and with these defects, their shape, and we define the square root of area in perpendicular to the principal maximum stress. And with this, we transform this defect into an equivalent crack, and we go on our key diagrams modified by the KT to make the evaluation of the expected fatigue strength in presence of defect, probability of survival of 50%. Then we have our T sigma for the dispersion, and so we calculate with high diagram usual this, our customers.
Okay. Some other questions? I have another one. You suggested a new method of standardization. And what are your next steps?
No, the first step, I presented a document that is called NZFR, that is my code, 03, to the IEN committee, IENTC 190, working group 7, that is now reviewing the IEN standard. And this is now submitted to our colleagues, and should be a document that will improve the new standards. At the same time, in Italy, with our UNCIDA standardization body, we started to make a new deal for own standardization in Italy to speed this way.